Solving exponential equations and logarithmic equations. Some of the log equations are kind of weird, but there's really nothing new to teach you here. It's all just using the rules of logarithms. But I'm going to do a bunch of examples later in the video, but there are a couple of new things here I want to talk about first. When you solve an exponential equation like 2 to the x equals 2 to the 3x plus 4, it turns out to be fairly simple, as long as the bases are the same. That's the important thing. If you weren't paying attention, you could take the log of both sides. That works when you solve an exponential equation. The log of 2 to the x equals the log of 2 to the 3x plus 4. We could use our log rules to take the exponent and move the exponent down in front. We'd have x times the log of 2 equals 3x plus 4, I'll put that in parentheses, times the log of 2. Notice there's the log of 2 on both sides. That's some decimal. We could divide both sides by the log of 2, and those would cancel. Anything divided by itself is 1, and it's just x equals 3x plus 4. Hey, look at that. X equals 3x plus 4. That's all I needed to do. Subtract 3x from each side. Negative 2x equals 4. Divide by negative 2. And x equals negative 2. Notice I can plug this in, and it makes it true. 2 to the negative second would equal 2 to the 3 times negative 2, which is negative 6, plus 4, which also is negative 2. It's 2 to the negative 2 equals 2 to the negative 2. And the important thing I want you to realize, as long as the bases are the same, all I need to do is set those exponents equal. X equals 3x plus 4, and solve, just like I did here, and you're going to get x equals negative 2. A log equation, like the log base 2 of x plus 5 equals the log base 2 of 15, in the same way, as long as the bases are the same, this turns out to be fairly simple to solve. But if you weren't paying attention, you might use the log rules, and what you would do then, there are probably a variety of ways you could solve this, but you could move this on the other side, minus, subtract it from both sides, the log base 2 of 15, and then that would equal 0. Then you could use your log rules. When do you subtract your exponents? Well, that's when you're dividing. This is the log base 2 of x plus 5 over 15 equals 0. Yeah, you could turn this into an exponential equation. 2 to the power of 0, remember a log is equal to an exponent. 2 to the 0 is equal to x plus 5 over 15. We know what 2 to the 0th is. Anything to the 0th power is 1. 1 equals x plus 5 over 15. Let's put that over 1 and cross multiply. 1 times x plus 5, x plus 5. 1 times 15 is 15. Oh, look at that. X plus 5 equals 15. X plus 5 equals 15. Subtract 5 from each side, and x equals 10. So, of course, I didn't need to do all this fancy stuff here. As long as the bases are the same, I could just say x plus 5 equals 15, like I did right here, and solve and get x equals 10. I want to point out that sometimes in these exponential equations, it's not apparent that you can solve them with that same base idea. But, like in this one, as an example, both 4 and 32 are powers of 2. 4 is 2 squared, and 32 is 2 to the 5th. So the way to solve this is to make those bases the same. 2 squared is what 4 is, and that's to the 2x power. And that equals 32, which is 2 to the 5th, which is to the 1/2 power. Now I have to remember my rules of exponents. Remember how x cubed squared is x to the 6th. When you have a power to a power or a power of a power, you multiply your exponents. That's the rule. That's how we get 6. So we'll use that here. This is 2 to the 4x equals 2 to the 5 halves. Yes, that's 2.5. I have the same base. Now I just need to set those exponents equal. 4x equals 5 halves, and you could use 2.5. Rather than divide by 4, I'm going to multiply by 1/4. That will allow me to cancel, get x by itself, and I get 5/8. Now you can use a decimal there as long as you're not rounding, and that's okay with me. Some questions may ask you to round, and in that case it's okay. But this is the same thing as 0.625. Either one of these are exactly the same thing. Some questions might ask for a fraction, some might ask for a decimal. Here you have another exponential equation that, again, it's not obvious that you can write those as the same base, especially the 1/4. And that's where you've got to remember what a negative power is. Remember how 3 to the negative second is 1 over 3 to the second, which is 1/9. That negative power doesn't mean it's negative, it means reciprocal. If I say 2 to the negative second, that's 1 over 2 to the second, which is 1/4. Hey, look at that. 2 to the negative second is 1/4. By the way, that's completely logical. Just to point out, if you say x to the 5th times x to the negative second, remember how when you multiply, you add your powers? Of course, this is x cubed. But if I apply this little idea here, the reciprocal idea, this would be x to the 5th times 1 over x squared. And we know that when we're multiplying, we can cancel. We can cancel 2 x's here and 2 here, and there's going to be 3 left, and I get that x cubed because this is really below. In effect, it's canceling. When you add those two together, you're canceling 2 x's. That's how we get that x cubed. Just remember that negative power means reciprocal. When you look at this question then, these are both powers of 2. This is 2 to the negative second, that's 1/4 to the x. And this is 2 to the third, which is 8 to the x minus 1. And we'll use that power of a power idea and we'll multiply our exponents. Don't forget to distribute right here. This becomes 2 to the negative 2x equals 2 to the distribute 3x minus 3. We have the same base. They're both base 2. We can just set those exponents equal. Negative 2x equals 3x minus 3. Now let's take a 3x from each side. Running out of room here. We get negative 5x equals negative 3, and we'll divide by negative 5, and x will equal 3/5, or 0.6. Notice that 2 negatives make a positive. We're going to solve a bunch of these on our next assignment, but I want to introduce the idea now, and you may run into this here. Turns out there's an easier way to do this with logs. We're solving for an exponent. That's how we know that we're going to be using logarithms. We're going to solve this question with logarithms. At 8% interest compounded annually, how long until 15,000 becomes 100,000? We are starting with, that's our start, our y-intercept, 15,000. Our interest rate is 8%. That's 1 plus 0.08 or 1.08. And we want to know how long. That's our x, it's time. This is what we're trying to find, time. And we want to get 100,000 out of this investment. if it was me, you can work with these numbers, that's fine. But I would probably divide both sides by 1,000, and you could, of course, they're going to be divisible by 5 also, but I just want to shrink the numbers down a little bit. I'm going to divide by 1,000, and I get 100 equals 15 times 1.08 to the x. As I said, you could keep simplifying. Divide both by 5. That would work. This is small enough. I'm just going to use this for my equation. To solve an exponential equation, we take the log of each side. The log of 100, which you can figure out, by the way. 10 to some power is 100. It would be 2. I'm going to leave it as it is. The log of 100 equals the log of 15 times 1.08 to the x. I guess I'll put this in parentheses. First thing you need to understand, this is super important. You cannot bring that x down. You can't bring it down. And the reason is you have an a times a b here. And we know that the log of ab equals the log of a plus the log of b. Yes. In order to bring the x down, I need to split up these two pieces because I have two things multiplied. In other words, I got to turn this into the log of 100 equals the log of 15 plus the log of 1.08 to the power of x. Now I can bring this down. I couldn't do it here because I had two things multiplied, but I can combine a couple of steps here. I need to solve for x, and when I bring it down, I'm going to have to move this to the other side because I need to get this piece by itself in order to divide and solve. So what I'm going to do to save some time here is I'm going to subtract the log of 15 from each side, minus the log of 15. And we get the log of 100 minus the log of 15 equals, I'm bringing that x down, x times the log of 1.08. Because I have times right here, all I need to do then is divide both sides by the log of 1.08. Put this in the calculator, and x will equal whatever that is. Be careful that when you put it in the calculator or Desmos, that you have parentheses around this so that you subtract before you divide. Remember that x is time, so it's going to take about 24, I'm going to round to the 10th, 24.7 years. You might have heard me say, yes, there's an easier way to do this with logs. Here's how to do it. In order to avoid that step where I had to split up the two because there were two things multiplied, and the two things multiplied are right here, the 1500 and the 1.08 to the x. The easiest way to do this with logs is to immediately divide both sides by 15,000. And that gets rid of the two things that are multiplied there, and you won't have to split that up. Now, if you punch this into Desmos, you could just reduce it as a fraction, or you could go back to what we had, which was 115. By the way, if you completely reduce that, it's 20/3, which is great too. Or you could just leave it like it is. It's not going to matter. It's just more numbers to punch in when you use your calculator or Desmos. This is 1.08 to the x. Now I can take the log of both sides. The log of 100 divided by 15, as I said, that reduces to 20/3, equals, and when I take the log of this side, I could just move the x down because it's a single thing there. X times the log of 1.08. And now I can just divide both sides by the log of 1.08 and put this into the calculator or Desmos, and I will get that same answer right there, 24.7 years. The rest of this video is questions from your assignment. I'm going to warn you that some of these log equations are completely confusing, and you need to see a few examples of them to understand. So as you go through your assignment, you're going to get to some that you get stuck on, guaranteed. Fast forward ahead in this video and find that question or a question close to it, and you should be able to find a similar example. Question 9, the like basis property and exponents. Use that to solve this equation. Notice how the bases are the same. All you need to do in this situation is set x minus 7 equal to 3x minus 3 and solve for x. How about I'll take an x off each side. Negative 7 equals 2x minus 3. And I'll add 3 to both sides. 2x equals negative 4. Divide by 2. Look at that. X is negative 2. Question 10. Use the like basis property. We need to write these with the same base. 8 is a power of 2, so is 16. 16 to the x equals 1/8. This is 2 to the power of 4 to the x. And this is 2 to the power of negative 3. That negative is how I do the reciprocal. Since the bases are the same, I can now set the exponents equal. 4x equals negative 3, divide by 4, and x is negative 3/4. A decimal works here. You could use negative 0.75 if you want. You could also punch this in the calculator, check it. 16 to the negative 3/4 or negative 0.75 should equal 1/8. Question 11. 1/5 and 5 I can write with the same base because 1/5 is 5 to the negative first. Remember that 5 to the negative first is 1 over 5 to the first power, which is 1/5. 5 to the negative first to the x plus 3 equals 5 to the 7x plus 10. I need to distribute there. That's 5 to the negative x minus 3. If I distribute negative 1, equals 5 to the 7x plus 10. And now that the bases are the same, I can set the exponents equal. Negative x minus 3 equals 7x plus 10. How about we add an x to both sides? Negative 3 equals 8x plus 10. And get the x by itself, take a 10 off. Negative 13 equals 8x, and divide by 8. And looks like it's negative 13/8. We could use the change base rule to solve this, but I think we can solve it without the change base rule. I'll show it both ways. I'm going to try to write 32 as a power of something that I can work with a base of 4. And what I'm thinking right now is that I could write this as the log base 4 of 2 to the 5th. Then I can bring that down. That would be 5 times the log base 4 of 2. Now when I look at this, this means 4 to some power is 2. Remember how the square root of 64 was the same thing as 64 to the 1/2? And the square root of 100 is the same thing as 100 to the 1/2. That's going to be 10, and that's going to be 8. Well, 4 to the 1/2 power is 2, because the square root of 4 is 2. This then is just 5 times 1/2, or 5/2. And it may ask for a fraction here, which you'd have to put in 5/2, but technically 2.5 is the same thing. You'll have to see what it asks for. What about the change base rule? How would I do that? I could say the log base 4 of 32 equals y. As an exponential expression, this is 4 to the power of y equals 32. Then I could take the log of both sides, and I'm going to use log 10 because I can use a calculator for that. The log of 4 to the y, and I can bring that y down now, is the log of 32. Y times the log of 4 equals the log of 32. And we'll just divide both sides by the log of 4. And this should end up being 2.5, which is 5/2 as a fraction. Note that if you want to save yourself some time, look at this and look how we solved it. It was the log of 32 divided by the log of 4. That's the change base rule. The log of 32 divided by the log of 4. Many of these questions, the way to solve them is to write the log as an exponential equation. Remember that the log base b of a equals c is the same thing. This implies that b to the power of c equals a. Note that the base is b. A log is an exponent. It's equal to an exponent. So we got c is our exponent, and it's equal to a. Right here, then, it's 3 to the power of 4 equals x minus 15. 3 to the 4th is 81 equals x minus 15. And all we need to do is add 15 to both sides. And x is 96. Another one, same idea. 2 to the 6th power is equal to x squared. 2 to the 6th is 64 equals x squared. We'll square root both sides and put our plus and minus out in front. And x is plus or minus 8. So that would be 8 comma negative 8. While we're at it here, note that you can't take the log of a negative number. If I gave you a question like the log of negative 5 equals x, is that possible? Can we find x? Notice that this would be base 10, there's no base, and this would imply that 10 to some power equals a negative number. There's no way to make an exponent turn a number into a negative. If it's a negative exponent, remember that's reciprocal. It doesn't make the number negative. Now, if the base was negative, I suppose that might work. But you'll notice that if you plug in a negative number and you hit the log of negative 2, for example, it says error, non-real answer. We can't do that. So we can't take the log of a negative number. However, here it's x squared. And if I plug in negative 8 and I square it, it becomes positive 64. The negative does work here because it's being squared. When you plug it in, it becomes positive. On question 19, we need to use our log rules. You know that when you add your exponents, that's when you're multiplying. The log of AB is equal to the log of A plus the log of B. In other words, I'm going to turn this into the log base 2 of 4x. This works because the bases are the same. We can't do this unless the bases are the same. It's the log base 2 of 4x equals 10. Turn this into an exponential expression. 2 to the power of 10 equals 4x. And 2 to the power of 10, calculator time, is 1024. 1024 equals 4x. Divide by 4, and x is 256. Question 20. In this case, we're subtracting. When do you subtract your exponents? That's when you're dividing. We know that the log of a divided by b, I'm using base 10. As long as the base is the same throughout the question, you're good. This is the log of a minus the log of b. We're going to take this and turn it into that. This is the log of 16 over x base 2 equals 10. Our base is 2. 2 to the 10th power is equal to 16 over x. We just did 2 to the 10th power is 1024 is equal to 16 over x. Let's cross multiply. 16 equals x times 1024, and we'll divide by 1024. And there's my answer, but I'm guessing this reduces. You could go to Desmos, put that in, and hit the little circle next to the problem you're typing in, and it'll reduce that fraction. 16 divided by 1024 as a reduced fraction is 1/64. Question 21. We're adding. These are exponents. When do you add your exponents? That's when you're multiplying. This is going to be an interesting one. This will be the log base 2 of x times x minus 3 equals 2. This is the log base 2 of x squared minus 3x equals 2. This means 2, the base, to the exponent of 2 equals x squared minus 3x. Looks like a quadratic. Let's get it equal to 0. X squared minus 3x minus 4 equals 0 because 2 squared is 4. And I moved it over there, and I subtracted it to move it. This factors, I'm betting. X times x is x squared. This number times this number makes -4. So it's a positive times a negative. I need factors of 4. One's positive, one's negative. So they're going to subtract to 3. That's 1 and 4. But when I place them, I need to make them add to -3, which is -4 and +1. Our answers then are x equals -1 and x equals 4. Those are the values you plug in that make 0. Now notice, if I plug in the log base 2 of -1, it doesn't matter what the base is, this isn't possible. It doesn't work. You get an error. The log of -1 is a non-real answer, calculator says to me. This does not work if you plug it in right here. We toss it, and it looks like 4 then is our only answer. Question 23 is a quick one. 2, the base to the power of 2, the exponent, is equal to x minus 32. 4 is x minus 32. Let's add 32 to both sides, and x is 36. Question 25. We're going to try to find the base of this log that makes this a true expression. Let's write it as an exponential expression. W, the base, to the exponent of -2 equals 1 over 25. Remember what the negative exponent means. When we say 3 to the negative second, it's 1 over 3 to the second. Yes, that's 1/9. X to the negative third is 1 over x to the third. This then is 1 over w squared, and that equals 1 over 25. Now you can cross multiply if you like. 1 times w squared is w squared. 1 times 25 is 25. W squared is 25. We'll take the square root of both sides. And technically, you would have a plus or minus here, but it says that w is greater than 0, so no negative. Don't worry about the negative. The square root of 25 is 5. We don't worry about the negative. There's our answer. The base would be 5. Question 26. I'm thinking this is a tricky one. We're subtracting. When do you subtract your exponents? That's when you're dividing. This is equal to the log of x plus 4 divided by x plus 1, and that equals 1. There is no base. This is base 10. This means that 10, the base, to the exponent of 1 is equal to x plus 4 over x plus 1. That means that x plus 4 over x plus 1 is equal to 10. Let's put that over 1 and cross multiply. X plus 4 times 1 is x plus 4. 10 times x plus 1, we need to distribute there. So it's x plus 4 equals 10x plus 10. Let's take an x off each side. 4 equals 9x plus 10. Let's take a 10 off each side. We're getting that x by itself. Negative 6 equals 9x. And divide by 9. And x is by itself. Looks like x 6/9 are both divisible by 3. Negative 2/3. And you have to be careful. You got to check. When I plug this in, is it going to create a negative number that I can't take the log of? Notice if I put negative 2/3 in here and I add 1, it becomes a positive number, positive 1/3. So that's okay. I can take the log of 1/3. Right here, if I plug in negative 2/3, it's negative 2/3 plus 4, which is 3 1/3. And again, I can take the log of that. This appears to work. Here's our answer. Question 27. This one looks a little crazy. I'm thinking we need to get this by itself on one side so that we can combine it. Let's move this over here. And we have the log base 8 of 10x plus 6 minus the log base 8 of negative 9x plus 6 equals 1/3. Now I'm going to combine those two, and I know when I subtract my exponents, that's when I'm dividing. This is the log base 8 of 10x plus 6 divided by negative 9x plus 6, and that equals 1/3. Let's turn this into an exponential equation. 8 to the power of 1/3 equals 10x plus 6 divided by negative 9x plus 6. This is something we've just learned about recently, those fractional exponents. Remember how when we say the square root of 100, there's a little tiny 2 here that we don't write, but it's understood to be there. And that little 2 is telling us that we need the number multiplied twice makes 100. That's the same thing as 100 to the 1/2 power. The cube root of 27 is the same thing as 27 to the 1/3 power. And the fourth root of 16 is the same thing as 16 to the 1/4 power. So the fifth root would be 1/5 power. The sixth root would be 1/6 power. That's the way it works. This is the number, this last one, The number that multiplied 4 times makes 16, it's 2. And 27 to the 1/3 is the number multiplied 3 times makes 27, which is 3. And of course, 100, the square root of 100, the number multiplied twice that makes 100 is 10. This then is the cube root of 8, which is 2. We have 2 equals 10x plus 6 over negative 9x plus 6. Let's put that over 1 and cross multiply. 1 times 10x plus 6 is 10x plus 6. And 2 times, don't forget that was a negative, 2 times negative 9x plus 6. I'm going to distribute right now. I'm going to take 2 to both. It's negative 18x plus 12. Let's add 18x to both sides. I'm going to move that 18x over there. That's going to be 28x plus 6 equals 12. Let's subtract 6 from both sides. We have 28x equals 6. And divide by 28. This is a fraction that simplifies to both divisible by 2 at the very least. That would be 3 over 14. And there's my answer. I think question 29 is a bit easier than the last one. Let's see. I'm going to combine these two. When do we add our exponents? That's when we're multiplying. This is the log of x plus 10 equals, over here it'll be the log of 10x. This is like the example I did early in the teaching where these two have the same bases. The only way those things can be equal is if x plus 10 is the same thing as 10x. Subtract an x from each side. 10 equals 9x, and divide by 9. Looks like x is 10/9. Question 30. Let's turn this into an exponential equation. 4 to the power of 1/2 equals x squared plus 1x, which is x. 4 to the 1/2 power, that's the same thing as the square root of 4. That's 2. 2 equals x squared plus x. Let's get this thing equal to 0 and move the 2 over here. It'll be x squared plus x minus 2 equals 0. Let's factor this thing. X times x is x squared. This number times this number makes negative 2. It's a positive times a negative. We need two numbers that multiply to 2, but add to positive 1. And because one's negative and one's positive, you can think subtract to 1. Factors of 2 that subtract to 1 are 1 and 2. When you place them, you need to make them add to positive 1, which means it's going to be positive 2 and negative 1. And the solutions are the values you plug in that create 0, because 0 times anything is 0. X would be negative 2, and x would be 1. If I take negative 2 and plug it in right here, the question is, does it work? The log of, I'm putting in negative 2 squared plus 1 times negative 2, does that equal 1/2? This is base 4. This is the log, negative 2 squared is 4. 1 times negative 2 is negative 2. And 4 plus negative 2 is 2. And this is base 4 equals 1/2. And notice that if you take a base of 4 and you go 4, and the exponent is 1/2, 4 to the 1/2, that's a square root of 4, and yeah, that's 2. It works. Watch out for the negative answers. Be sure that you plug them in and check, and that they actually work. Our answers here then are negative 2 and 1.